Hi, this is Mrs. LaBarbera. This is AP Physics Mechanics C. Today I want to talk an example about conservation momentum, conservation of energy, and work-energy relationship. A 0.3 kilogram card moving at 2 meters per second to the right collides with 0.10 kilogram card, initially moving at 3 meters per second to the left. After the collision, 0.1 kilogram card moves to the right with a speed of 1.2 meters per second. Assume friction is negligible. Part A, calculate magnitude and the direction of the velocity of 0.3 kilogram card after collision. So this is collision problem. During collision, momentum is always conserved. P before equals to P after, but we need to track which a card is moving at what velocity. So I made a chart so I can keep track it. 0.3 kilograms moving to the right before, 0.1 kilograms moving to the left. That's why it's negative. This is after. After 0.1 kilograms moving to the right. And we need to find what is the speed after for 0.3 kilogram card. P before equals to P after. M1 V1 plus M2 V2 equals to M1 V1 prime plus M2 V2 prime. Plug all the numbers in, you'll have V equals to 0.6 meters per second to the right. In all your answers, you need to have units. And in this case, you also need direction. Part B, is this an elastic collision? Justify your answer. What is the definition of elastic collision? So in the elastic collision, all the kinetic energy is conserved. Kinetic energy of the system is conserved. That means kinetic energy before the collision equals kinetic energy after the collision. To check that, we have to calculate what is kinetic energy before. That's M1 times V1 squared plus M2 times V2 squared. M1 V1 squared plus M1 half M2 V2 squared. So I have 1.05 joules. Similarly, I can calculate total kinetic energy after M1 V1 squared, V1 prime squared plus M2 V2 prime squared. And I have 0.126. As you can see, those are not the same. That means collision is not elastic. Now the 0.3 kilogram card is not removed. The 0.1 kilogram card continues to move to the right and then collides with and compresses an ideal spring whose right end is attached to a fixed wall. Calculate potential energy of the spring when it reaches maximum compression. So when it reaches maximum compression, that means the car must stop. The speed has to stop. So all the kinetic energy of 0.1 kilogram card is converted into elastic potential energy of the spring. Energy is conserved in this case because the only force that's doing the work is force of the spring, which is a conservative force. Energy before equals to energy after. Energy before is kinetic. Energy after of the system is elastic in the spring. So we simply plug in the number. That's 1/2 kinetic energy is 0.1 kilogram card. Remember, use the correct card times the correct speed after the collision. So you'll have 0.072 joules. Part D, the maximum compression we know is 0.1 meters. What is the spring constant? So we know EL equals 1/2 kx squared. We know what x is. We know UEL, so we can figure out k. So k equals 2 UEL over x squared. Substitute the numbers in. And this one, you can also write this as joules per meter squared, which is the same as newtons per meter. Part E, suppose instead the spring is nonlinear. So that means F does not equal to Kx. That means UEL does not equal to 1/2 Kx squared. That's what nonlinear means, such that the force F due to the spring when it compresses the distance is F equals to negative bx cubed. Calculate value of constant B if the spring is compressed 0.10 meters. Because spring is a conservative force, so there is a relationship between potential energy and the conservative force, which is this. Change in potential energy equals negative work done by the conservative force. This change is UEL minus 0 because you started from rest. So there's no energy in the spring. You moved from 0 to 0.1 f dx. And what is f? F equals negative bx cubed. Negative and negative cancels, so it becomes b times x cubed. To integrate this, b is constant, and x cubed, the integral of x cubed is 1/4 x to the 4th minus x 0 to the 4th, which is 0. So UEL is 0.072 joules. And here's 1/4 b times 0.1 meters to the 4th. So from here we can solve for b. B equals to 2,880 joules per meter to the power of 4. This is the same as 2,880 Newton per meter cubed. That's it.